Okay, so let's add a little bit more to this idea of Rossby adjustment and the Rossby radius of deformation. Rossby radius of deformation is a length scale. L rho is written as G prime H over 2 omega. So we are still in this water tank setup, not on the sphere yet. So we are going to leave the rotation as 2 omega. The real world Rossby radius of deformation has exactly parallel expression as we will see. G prime is our reduced gravity, H is the vertical scale of motion, and N is related to G prime, the buoyancy frequency as it's called, or the Brent-Väisälä frequency. As I said, it's how the parcel behaves when it's displaced in the fluid and its buoyancy is perturbed. It may generate an oscillation, or it may just continue to sink or continue to rise depending on the buoyancy frequency. So it's NH divided by 2 omega. So LR, L rho again, the Rossby radius of deformation, is the horizontal length scale. Okay, so it is the scale at which effects of rotation become comparable to the effects of stratification, right? G prime is essentially our stratification, N is the stratification, and 2 omega or H is essentially our scale of rotation, effects of rotation, right? So just like we saw in the tank with the cylinder collapse, rotational effects balance the stratification effect in the situation where the other forces are not so significant. This matters in the real world because on scales smaller than the Rossby radius, smaller than where the rotational effects and stratification effects are balancing, the pressure field tends to adjust to the velocity field. This is like a perturbation coming in, so you can think of pressure field as a mass field in the atmosphere because of the hydrostatic balance, and velocity field is could be a warm front coming in, a cold front coming in, or a hurricane or whatever, right? So if the scales are much greater than L rho, Rossby radius of deformation, the perturbation coming in is much larger, then the velocity field adjusts to the pressure field. Okay, we'll show some examples to see how that works. The general magnitude of the Rossby radius of deformation in the atmosphere is about 1,000 kilometers, considering the stratification and the scale height, the scale of vertical scale of motion. It's not the scale of vertical motion, but it's the vertical scale of motion. Very different. In the ocean, it's 2 orders of magnitude smaller at 30 kilometers. Okay, we'll see that this tends to have strong constraints on perturbations. So here, think of a large scale disturbance where the initial disturbance is much larger than the Rossby radius of deformation. So here is 2 pi LR, and this is half of the length of the perturbation. Okay, so you can see that after the stratification and rotational effects have adjusted, the perturbation mass field is essentially maintained. So you can see that that's a pressure equals constant surface. So it's like a mass field, which means it's a pressure field. And winds have adjusted to the pressure field. Okay, so you have created a cyclonic circulation about this low pressure disturbance coming in at a very large scale, and perturbation size itself hardly changes. Okay, so those are the wind vectors. So a low pressure perturbance comes in, and it's so large that the local velocity field has to adjust to it and create a cyclonic circulation because it's a low pressure that's coming in. Sinking, remember the changes in the geopotential height, for example, right? Contours of height on pressure surfaces tell you about changes in velocity fields and so on. So if on the other hand small scale disturbances come in, so L in this case is much smaller than 2 pi LR, The 2 pi LR is here. Initial disturbance is fairly small on the P equals constant surface. Then the final adjustment looks like this, where the perturbation basically spreads out and looks much weaker. So here you have velocities that are fairly strong. Here they become weaker and spread out. And some winds are retained, so you still have the cyclonic circulation, but the mass field has adjusted to the winds. Okay, so what does this mean? Basically, if you have a tornado coming in, then the tornado basically gets spread out and wiped out eventually. I don't know if that's the exact analog, but I'm just trying to help you visualize. Okay, mass field, in other words, pressure heights are adjusted to the disturbance. Okay, that's kind of the control of the adjustment of the pressure field and the velocity field depending on the size relative to the Rossby radius of deformation. Will this work? Whoops, didn't work. So let me copy that and get out and get back into internet. Whoops, I just wanted to show the typical eddies in the atmosphere and the ocean. If it works, since I'm doing screen capture, it should work. Let's see. We had seen this animation before where we are showing advection or transport of aerosols. If I have internet working, this should come up sooner or later. But you see perturbations moving in the atmospheric circulation, background circulation, which end up creating these pressure and velocity field adjustments. Putting it on full screen, can I do that? Here we are. I don't know if it's clear or not. You can see these eddies swirling around and being transported by the background velocity field and so on. So the scale of these eddies is determined by the Rossby radius of adjustment. Okay, and remember that there is a F dependence on the Rossby radius, so obviously that's going to change with altitude. It's in the denominator, so it's going to decrease in the latitude, not altitude, latitude. Okay, why does it matter? Basically because if you are doing weather predictions or ocean circulation or whatever, if you want to capture these kind of features which are important for transporting humidity, aerosols, chemicals, etc., then you want to have the ability, the model should be having the grid size that is small enough compared to the Rossby radius of deformation to be able to capture those features that are important. The other animation is for the ocean. Ocean is also full of eddies, and it's not always clear exactly what the eddies do, but they do produce biological features, tracer features. This one has music, so I'll stop talking once it starts playing. But the main thing you'll notice is that there are eddies of various sizes all over the ocean. This runs for 3 minutes. I'm not going to let it run for the whole period, but eddies are generated by nonlinearities in the system. If it continues to play, okay, there we are. So you can see that these eddies, they are directly related to the Rossby radius of deformation in the Gulf of Mexico, for example, because maybe I can reduce this. Yes, so because the Rossby radius of deformation, which depends on rotation, hence latitude and stratification. So you can see these rings are being shed in various places. The Southern Ocean is full of rings and eddies. This is the Agulhas outflow coming from the Indian Ocean Mozambique Channel. Some of it returns, some of it goes off into the Atlantic Ocean, and so on and so forth. As I said, I won't let it run the whole time, but you can watch it on YouTube. This is available. So every time you have nonlinearities in the flow, you get eddies shedding. It's called shedding of eddies, and the size of the eddies depends on the Rossby radius of deformation. Okay, that's how useful the Rossby radius of deformation is.